NASA just did something they almost never do. They stopped searching for new planets. Think about that for a moment. An entire satellite designed and launched specifically to discover worlds orbiting distant stars suddenly went silent on its primary mission. Instead, it focused its cameras on a single object racing through our solar system. One comet. That's all it took to pause its main mission. Stay with me. In the next few minutes, we're going to uncover exactly why this comet commanded such extraordinary attention, what scientists discovered when they finally got their instruments locked onto it, and why this visitor from beyond our solar system might be carrying secrets that change how we understand our place in the universe. The satellite in question is called TESS, the Transiting Exoplanet Survey Satellite. For years, it's been humanity's tireless hunter scanning the cosmos for the telltale dimming of starlight that betrays a planet passing in front of its sun. It has discovered thousands of planet candidates, some scorching hot, some frozen solid, some that might, just might, harbour the conditions for life. This is what TESS does. This is what it was built for. So when NASA made the decision to pause that mission, to swing TESS's gaze away from distant stars and focus instead on something much closer to home, the scientific community took notice. The object that captured their attention bears a designation that tells its own story. 3I/Atlas. That I stands for interstellar. This isn't some ordinary chunk of ice and rock making another predictable lap around our sun. This visitor comes from somewhere else entirely, another star system. Another corner of the galaxy. It travelled through the vast emptiness between stars for longer than human civilization has existed, and now, for just a brief moment in cosmic time, its path intersects with ours. We've only confirmed 3 of these interstellar visitors in all of human history. 3. The first arrived in late 2017 and sparked debates that continue to this day. The second came in 2019 and looked strangely familiar, like comets we've known all along. Now this third traveller passes through, and something about it made NASA decide that hunting for distant planets could wait. The comet couldn't. Here's what you need to understand. Space agencies don't make decisions like this lightly. Every minute of observation time on spacecraft like TESS is planned months, sometimes years in advance. Scientists compete fiercely for access to these instruments. Proposals are written, reviewed, debated. Priorities are weighed against each other with excruciating care. The idea of simply interrupting all of that, of telling researchers around the world that their approved observations would have to wait because something unexpected demanded immediate attention, goes against every instinct of careful planning that governs space exploration. But they did it anyway. In January of this year, as 3I/Atlas made its outbound journey from the inner solar system, TESS stopped looking for planets. For over a week, it watched this comet continuously, measuring every flicker of light, every subtle change in brightness, building a detailed picture of an object that would soon leave our solar system forever. And here's something that makes this even more remarkable. Scientists later discovered that TESS had actually glimpsed this comet months earlier, in earlier archived data, before anyone even knew it was there. The data sat in archives, waiting to be noticed, holding clues that would only make sense once we understood what we were looking at. What could possibly justify such a dramatic shift in priorities? What makes one comet, even an interstellar one, important enough to set aside the search for new worlds? The answer lies not just in what 3I/Atlas is, but in what it represents. Every object that visits us from interstellar space is like a message in a bottle, thrown into the cosmic ocean by processes we're only beginning to understand. These visitors carry information about places we cannot reach, cannot visit, can barely imagine. They are our only physical samples of the universe beyond our sun's influence. When 3I/Atlas appeared in our telescopes, astronomers recognized immediately that they were looking at something precious, a gift, an opportunity that wouldn't come again in their lifetimes. This comet would spend mere months within reach of our instruments before departing forever, and every observation mattered. Every measurement counted. Every piece of data collected would become part of humanity's permanent record of this encounter. There would be no second chances, no return visits, no opportunity to go back and study something they'd missed the first time. So NASA made the call. The planet hunting could wait. This could not. Now, before we go deeper into what makes 3I/Atlas so special, I want to ask you something. If this story has caught your attention, if you're curious about what scientists found when they turned TESS toward this ancient traveller, Do me a favour, hit that like button. Let me know this content matters to you. Subscribe if you want to journey through more mysteries like this one, because the universe is full of them, and we're living in an age where we can actually investigate these cosmic puzzles with real instruments, real data, real discoveries. And drop a comment telling me where you're watching from. Are you under the same sky this comet passed through? Because wherever you are on this planet, you share something with everyone else right now. We all witnessed the same visitor passing through our cosmic neighbourhood. The story of 3i/Atlas isn't just about one comet, it's about the broader revolution happening in astronomy right now, where we're learning that our solar system isn't as isolated as we once thought. The space between stars isn't empty. It's filled with wanderers, with objects ejected from their home systems, drifting through the galaxy, occasionally passing through our neighbourhood like travellers on an endless road. For most of human history, we didn't know these visitors existed. We couldn't detect them. Our telescopes weren't powerful enough. Our survey systems weren't comprehensive enough. We simply missed them as they passed silently through, invisible against the backdrop of stars. That changed less than a decade ago. In 2017, telescopes in Hawaii caught something that shouldn't have been there. An object moving too fast on a trajectory that defied explanation. It wasn't orbiting the sun. It was passing through, like a car speeding through an intersection without stopping. That object, later named Oumuamua, opened our eyes. We realized the universe had been sending us visitors all along. We'd just never noticed before. Since then, we've been watching more carefully, building better survey systems, training our instruments to recognize these cosmic travelers. And now, with 3i/Atlas, we're getting better at it. We're not just detecting these visitors anymore, we're studying them, learning from them, extracting their secrets before they vanish back into the darkness. But what secrets does a comet carry? What can a chunk of ice and rock, even one from another star system, really tell us that justifies stopping the search for planets? The answer to that question is what makes this story fascinating, and it's where we're heading next. Because 3i/Atlas isn't just any interstellar visitor, it's behaving in ways that surprise scientists, revealing characteristics that challenge assumptions, carrying clues about its origin that paint a picture of a place and time unimaginably distant from here and now. To understand why this matters, we need to step back and look at the bigger picture. We need to understand what it means for something to be interstellar in the first place. How does an object end up wandering between stars? Where did 3i/Atlas come from? How long has it been travelling? And what does its presence here, in our solar system, tell us about the galaxy we live in? These questions don't have simple answers, but they have compelling ones. Answers that connect this single comet to the deepest questions we ask about existence itself. About how planetary systems form, how common they are, whether the ingredients for life are sprinkled throughout the cosmos or confined to rare pockets of fertility. So let's follow this visitor back to its origins. Let's trace its path through space and time. Let's understand what it means to be a traveller from another star. The discovery of something truly extraordinary rarely announces itself with fanfare. There are no sirens, no flashing lights, no dramatic countdown to revelation. Instead, it usually begins with someone noticing that the numbers don't quite add up, a data point that sits slightly wrong, an observation that doesn't match expectations, a puzzle that demands attention simply because it refuses to fit into the neat categories we've created for understanding the universe. For 3i/Atlas, that moment came through the patient work of astronomers monitoring the sky with a network of telescopes designed to spot things that change or move. The Atlas system, spread across observatories in Chile and Hawaii, operates like a cosmic security camera, photographing the same patches of sky over and over, night after night. Software compares each new image to previous ones, flagging anything that's moved or brightened or appeared where nothing existed before. Most of these alerts are known objects going about their business, asteroids in their eternal orbits, comets we've tracked for years, satellites reflecting sunlight. But occasionally, rarely, something appears that the system doesn't recognize. When the alerts first came in about an object moving through the constellation Sagittarius, astronomers followed standard procedure. They checked existing databases, they calculated preliminary orbits, they tried to match this moving point of light to known comets or asteroids that might be in that region of sky. Nothing matched. The object was new, which isn't particularly unusual. We discover new asteroids and comets regularly as our survey capabilities improve. What made this different was the trajectory. as more observations accumulated over subsequent nights, allowing for better orbital calculations, something remarkable emerged from the mathematics. This object wasn't following the usual rules. Every comet and asteroid born in our solar system moves on a path shaped by the sun's gravity. They orbit, whether in tight circles or elongated ellipses, forever bound to the star that dominates our cosmic neighbourhood. Even the most distant objects, so the ones that venture far beyond Pluto into the frozen outer reaches, eventually turn around and fall back toward the sun. Their orbits are closed loops, but the numbers coming back from 3I/Atlas told a different story. Its path wasn't a closed loop, it was a hyperbola, a mathematical curve that enters once and never returns. Imagine throwing a ball straight up into the air. No matter how hard you throw it, Earth's gravity will eventually slow it down, stop it, and pull it back down. That's a closed orbit. Now imagine throwing that ball so hard that it escapes Earth's gravity entirely, sailing off into space, never to return. That's a hyperbolic trajectory. That's what 3I/Atlas was doing with respect to the Sun. It was moving too fast. The Sun's gravity, immense as it is, couldn't capture it. This object was just passing through. The implications hit the astronomical community quickly. Interstellar. It had to be. No object born orbiting our Sun moves this way. The only explanation was that 3I/Atlas came from somewhere else, arrived with enough speed to pass through our solar system without being captured, and would eventually leave, continuing its journey through the galaxy. This realization transformed what had been routine observations of a new comet into something far more significant. Every telescope that could be brought to bear on this visitor suddenly became vital. Time was finite. The comet wouldn't wait for leisurely study. But here's where the story gets interesting. Determining that something is interstellar is just the beginning. The real questions come next. Where did it come from? When did it start its journey? What can it tell us about the place it left behind? These questions require detective work of the highest order, piecing together clues from limited data, making educated inferences from fragmentary evidence. The trajectory analysis provided the first clues. By tracing 3I/Atlas's path backward through space, astronomers could determine which direction it came from. The answer pointed toward the constellation Sagittarius, toward the thick disk of our galaxy, where stars cluster more densely than in our local neighbourhood. This region, rich with stellar systems, represents a vast nursery of planets and comets and asteroids, all the debris that accompanies star formation. Somewhere in that direction, likely thousands of light years away, 3I/Atlas began its existence. It formed around another star. It orbited in another planetary system. It knew a different sun than ours. What happened to eject it from its home? This question haunts every interstellar object we discover. Comets don't just decide to leave their star systems, they need help. Something has to throw them out with enough violence to overcome their star's gravitational hold. In our own solar system, we understand this process reasonably well. Large planets, particularly Jupiter with its immense gravity, occasionally fling comets onto paths that send them out of the solar system entirely. A comet makes a close pass by Jupiter. The gravitational interaction acts like a slingshot, and suddenly the comet is moving fast enough to escape the Sun forever. The same process likely happened to 3I/Atlas, but billions of years ago and thousands of light years away. Some planetary giant in its home system pulled it close, accelerated it, and threw it out into interstellar space. From that moment, it became a wanderer, no longer bound to any star. Moving through the dark spaces between stellar systems at speeds that seem fast by human standards, but are glacially slow on cosmic scales. For millions, perhaps billions of years, it drifted. The galaxy rotated beneath it. Stars formed and died along its path. Civilizations might have risen and fallen on planets, orbiting stars it passed, though at such enormous distances that neither the comet nor those civilizations would ever have known about each other. And then, by pure chance, its path intersected with our solar system. This intersection isn't destiny. It's statistics. The galaxy contains hundreds of billions of stars, and the spaces between them, while vast, aren't infinite. Objects wandering through those spaces will occasionally encounter stellar systems, the way a person walking through a forest will occasionally pass near a tree. For 3I/Atlas, our Sun was that tree. Our solar system was the clearing it happened to wander into, and we, the inhabitants of one small planet orbiting that Sun, happened to be watching at the right time with the right instruments to notice it passing through. The discovery wasn't just about spotting a moving point of light. It was about recognizing significance, about understanding that this particular moving point carried information from beyond our cosmic neighborhood, about realizing that we had a limited window to study something that would never return. The astronomers who first calculated its hyperbolic trajectory understood this immediately. They began the process of alerting colleagues, requesting additional observations, coordinating efforts across multiple observatories and space agencies. Word spread through the astronomical community with the speed that important discoveries always generate. Research groups shifted their schedules, observatories adjusted their plans, space agencies evaluated their assets, asking which spacecraft might have useful viewing angles, which instruments might capture meaningful data. This coordination, this sudden focusing of global scientific attention on a single object, represents one of the beautiful aspects of modern astronomy. National boundaries dissolve. Competitive instincts give way to collaborative urgency. Everyone understands that the universe has offered a gift, and the only proper response is to extract every possible insight before the opportunity vanishes. 3. I/Atlas had been discovered. Its interstellar nature had been confirmed. Its trajectory had been calculated. Now came the real work, figuring out what secrets this ancient traveller carried, and whether those secrets could teach us something new about the universe beyond our small corner of it. The comet was approaching the inner solar system, where the sun's heat would awaken it from its frozen dormancy, causing it to release gas and dust that instruments could analyze. Scientists knew they had months, not years, to conduct their studies. They knew that every observation mattered, and they knew that NASA's decision to redirect TESS to interrupt planet hunting for this visitor represented a recognition of just how rare and valuable this opportunity truly was. The discovery story of 3I/Atlas is more than a tale of astronomical detective work. It's a reminder that the universe still holds surprises, that even in an age of comprehensive sky surveys and powerful telescopes, nature can present us with phenomena we didn't predict. And it's a testament to human curiosity, to our refusal to let these cosmic visitors pass unnoticed through our neighborhood. We're no longer passive inhabitants of this solar system. We are active observers, reaching out with instruments and intelligence to touch, however briefly, the messengers that arrive from the galaxy beyond. What does it mean to be interstellar? The word carries weight, conjures images of vast darkness and impossible distances, but let's make it concrete. Let's understand what 3I/Atlas's journey actually represents in terms we can wrap our minds around. Start with the space between stars. We call it interstellar space, but emptiness might be a better word. It's not truly empty, of course. A few atoms of hydrogen per cubic meter, occasional molecules, traces of dust are so fine they barely register, but compared to the density of matter we experience on Earth, or even in the thin atmospheres of planets, interstellar space is as close to nothing as nature allows, and it's vast, incomprehensibly vast. The nearest star to our Sun sits more than 4 light-years away. That means light itself, travelling at nearly 300,000 kilometres every second, takes over 4 years to cross that gap. Nothing in human experience prepares us for distances like that. Into this emptiness, as billions of years ago 3I/Atlas was thrown. Whatever gravitational interaction ejected it from its home system sent it sailing into the dark with enough velocity to never return. From that moment it became a true wanderer. No star owned it. No planetary system claimed it. It moved through space following the subtle gravitational contours of the galaxy itself, responding to the collective pull of billions of stars rather than the dominant influence of one. The direction it came from tells part of its story: Sagittarius. When we look toward that constellation, we're looking toward the center of our galaxy, toward the dense disk where stars pack together more tightly than in our quiet suburban location. Our Sun sits in what astronomers call the galactic suburbs, out in one of the spiral arms far from the crowded center. It's a peaceful place, cosmically speaking. Stars are spread out. Gravitational interactions are gentle. We orbit the galactic center once every couple 100 million years, a stately waltz that's been going on since the solar system formed. But the region 3I/Atlas came from is more dynamic. Stars there are closer together. Gravitational influences are stronger. Interactions happen more frequently. It's the kind of environment where ejecting comets from planetary systems might occur more often, where the probability of these interstellar wanderers being created is higher. When 3I/Atlas left its home, whenever and wherever that was, it entered a galaxy full of motion. Everything orbits, everything moves. Stars circle the galactic centre, gas clouds flow along the spiral arms, and through it all, objects like 3I/Atlas drift, following paths that intersect, diverge, and occasionally bring them into regions like ours. The timescales involve defy intuition. How long has 3I/Atlas been travelling? We don't know precisely. The calculations are difficult because we can't trace its path perfectly backward through time. The galaxy's gravitational field is complex, constantly changing as stars move and gas clouds shift. But we can make educated estimates. Millions of years at least. Possibly billions. Imagine that. This chunk of ice and rock, no bigger than a mountain, has been drifting through space since before recognizable life emerged on Earth. It was already ancient when dinosaurs walked this planet. It predates human civilization by margins so large that our entire recorded history represents less than a blink in its journey. And all that time, it remained essentially unchanged. This is what makes interstellar objects so valuable scientifically. In the cold of interstellar space, far from any star's warmth, chemical processes essentially stop. Radioactive decay continues. Occasional impacts from other drifting material might alter the surface, but the deep interior, the core of 3I/Atlas, has remained frozen in time since its formation. It's a sample of ancient material, preserved by the perfect cold of space, carrying information about the conditions that existed when and where it formed. Compare that to objects in our solar system. Even in the frozen outer reaches beyond Neptune, the sun's distant warmth has some effect. Solar wind reaches out, a constant stream of charged particles that interacts with surface materials. Radiation from the sun, weak though it becomes at those distances, still causes slow chemical changes over billions of years. Objects in our solar system have been marinating in the sun's influence since they formed, but 3I/Atlas spent most of its existence far from any star's influence, preserved in a way that solar system objects cannot match. This preservation makes it a time capsule. When scientists analyze the gas and dust released as 3I/Atlas approaches the sun, when they measure its composition and study its chemistry, they're looking at a sample from another planetary system frozen in time. They're seeing what materials were present when that distant system formed. They're learning about the conditions that existed in that region of the galaxy billions of years ago. It's the closest thing we have to being able to reach out across the vast distances between stars and touch another world. The concept of being not bound by the sun's gravity deserves deeper understanding because it defines what interstellar means. Every comet born in our solar system, even those that venture out to enormous distances, remains gravitationally tied to the sun. Think of it like a yo-yo on a string. You can throw it out as far as the string allows, but eventually the string pulls it back. The sun's gravity is that string for solar system objects. They can move far away, but they're always being pulled back, always bound to return. But 3I/Atlas came into our solar system already moving fast enough that the sun's gravity, while it certainly affected the comet's path, couldn't capture it. The sun bent its trajectory. Sasa pulled it closer, accelerated it as it fell inward toward Perihelion, then watched it swing around and head back out. But that gravitational interaction wasn't enough to trap it in an orbit. The comet's speed remained above the escape velocity needed to leave the solar system. It's like throwing a ball so hard that even though Earth's gravity tries to pull it back, the ball has enough energy to keep going, to leave Earth's gravitational well entirely and sail off into space. This is what marks 3I/Atlas as different. Not just its composition, though that matters. Not just where it came from, though that's fascinating. But fundamentally, it's the trajectory. The mathematics of its motion declare unambiguously that this object came from outside and will return to outside. It's a visitor, not a resident. It's passing through our cosmic neighbourhood for a handful of months out of a journey measured in millions or billions of years. Think about what that means for observations. Every measurement taken, every spectrum captured, every image recorded, documents something that will never be available for study again. When 3I/Atlas leaves, it's gone. It won't come back in 100 years or 1,000 years or 1,000,000 years. Its path through the galaxy will take it to other regions, past other stars perhaps, but never again through our solar system. This single pass is our only opportunity, humanity's only chance to study this particular messenger from interstellar space. The recognition of this finality drives the urgency behind the observations. It explains why NASA redirected TESS. why observatories worldwide coordinated their efforts, why spacecraft that happened to have useful viewing angles were tasked with observations even if comet study wasn't part of their primary mission. Everyone involved understood the stakes. This wasn't like studying a planet that will be there next year and the year after. This was a no-one-ever proposition. Extract the data while the comet is within reach, or lose the opportunity forever. But 3I/Atlas isn't the first interstellar visitor to present us with this challenge. Before we dig deeper into what makes this particular comet special, we need context. We need to understand what came before, because the story of interstellar visitors is still being written, and 3I/Atlas is just the latest chapter in a narrative that began less than a decade ago, when our instruments first became powerful enough to detect these cosmic travellers as they passed through our neighbourhood. That earlier history, those previous visitors, they set the stage for understanding why 3I/Atlas matters and what its observations might teach us. Before 3I/Atlas, there were two confirmed interstellar visitors that arrived in our solar system, announced themselves through their impossible trajectories, and fundamentally changed how we think about the space between stars. Each taught us different lessons, each raised new questions, and together they created the framework for understanding what 3I/Atlas represents. The first arrived in October of 2017. The Pan-STARRS telescope in Hawaii spotted it, a faint point of light moving rapidly through the constellation Lyra. Initial calculations suggested it was an asteroid or comet, nothing particularly special. But as observations accumulated, astronomers realized they were looking at something unprecedented. The trajectory was wrong, too fast, too steeply angled. This object wasn't orbiting the Sun. It had come from interstellar space, passed through our solar system, and was now heading back out, moving too quickly for solar gravity to capture it. The astronomical community named it Oumuamua, a Hawaiian word meaning scout or messenger. The name fit. This was indeed a messenger from beyond our solar system, the first we'd ever confirmed. Excitement rippled through research institutions worldwide. Here was an actual sample from interstellar space, something they could point telescopes at, study, analyze. Scientists scrambled to gather data before it moved too far away. But Oumuamua was strange. Not just interstellar, which was remarkable enough, but strange in ways that spark debate still continuing today. Its shape, inferred from how its brightness changed as it tumbled through space, appeared extremely elongated. Some calculations suggested it might be 10 times longer than it was wide, like a cosmic cigar, or perhaps a thin pancake-viewed edgeon. Nothing in our solar system looks like that. Asteroids and comets are generally more rounded, more compact. This elongated shape defied easy explanation. Even stranger, Oumuamua showed no obvious signs of comet activity. When comets approach the Sun, heat vaporizes their icy surface, releasing gas and dust that forms the characteristic coma and tail we associate with comets. But Oumuamua, even when it passed relatively close to the Sun, remained stubbornly inactive. No coma, no tail. It looked like an asteroid, made of rock and metal rather than ice. Yet as it moved away from the Sun, careful measurements revealed it was accelerating slightly as if something was pushing it. Comets do this. The gas released from their surface acts like tiny rocket engines, giving them small accelerative nudges. But if Oumuamua was releasing gas, the effect was so subtle that no instruments could detect it. These contradictions sparked intense scientific discussion. Some researchers proposed exotic explanations. Maybe it was covered in a layer of organic material that prevented typical comet outgassing. Maybe its shape was even more unusual than initial calculations suggested. A few scientists explored artificial origins as one possibility among many, though the vast majority favour natural explanations and no evidence supports artificiality. The debates highlighted how little we understood about interstellar objects. We had exactly one example, and it didn't fit neatly into our existing categories. The questions Oumuamua raised remained unanswered as it sped away from the solar system. By the time the scientific community fully appreciated how unusual it was, the object had moved too far for detailed study. The opportunity passed. Telescopes lost track of it against the distant stars. Whatever secrets Oumuamua carried went with it, leaving astronomers frustrated but also energized. If one interstellar visitor had reached us, surely others would follow. The key was to watch more carefully. Now you'd have systems in place to detect the next visitor earlier, to maximize observation time before it departed. That next visitor arrived in August of 2019. An amateur astronomer named Gennady Borisov, working with a telescope he'd built himself, spotted an unusual object moving through Gemini. Professional astronomers quickly confirmed his discovery and calculated the trajectory. Interstellar. Again. This was 2I/Borisov, the second confirmed visitor from beyond our solar system. But Borisov was different from Oumuamua in almost every way. Where Oumuamua had been mysterious and enigmatic, Borisov was reassuringly familiar. It looked like a comet. It acted like a comet. As it approached the Sun, it developed a coma and tail just like comets born in our solar system. Spectroscopic analysis of the gas and dust it released showed compositions similar to solar system comets. Water vapor, carbon monoxide, other simple molecules we've detected in countless comets over decades of observation. The scientific community breathed a collective sigh of relief. Oumuamua might have been weird, but Borisov suggested that most interstellar comets are probably ordinary, at least in terms of composition and behavior. It implied that the processes forming comets around other stars produce results similar to what happens in our solar system. The chemistry might be universal. The physics governing planetary formation might operate the same way regardless of which star system you're looking at. Borisov also arrived with better timing. Discovered earlier in its passage through the solar system, that it gave astronomers more time to coordinate observations. Telescopes around the world tracked it. The Hubble Space Telescope captured detailed images. Ground-based observatories took spectra. By the time Borisov departed, scientists had amassed a substantial dataset far more comprehensive than what had been possible with Oumuamua. These two visitors, so different from each other, taught crucial lessons. First, interstellar objects do pass through our solar system with some regularity. We detected 2 within just a couple years once we started looking properly. This suggested that many more exist, passing through undetected, too small or too faint for our telescopes to spot. The space between stars might be filled with these wanderers, far more common than we'd previously imagined. Second, interstellar objects display diversity. Oumuamua and Borisov were nothing alike. One mysterious, one familiar, one inactive, one cometary. This diversity suggested that planetary systems throughout the galaxy produce a wide variety of objects, ejecting them into interstellar space through various mechanisms. Studying more visitors would give us statistical insight into what's typical and what's rare. Third, and perhaps most important, these visitors were scientifically accessible. With the right instruments and enough observation time, we could learn real things about them. Composition, structure, behavior. Each visitor added to our understanding of planetary formation beyond our solar system, giving us actual physical samples from places we could never visit directly. But 2 data points aren't enough to draw firm conclusions. 2 examples show that interstellar visitors exist and that they vary, but they don't establish patterns. They don't answer the deeper questions about how common these objects are, what range of compositions they display, or what their presence tells us about planetary systems throughout the galaxy. For that, we need more examples. We need to build a statistical sample. We need visitor number 3 and 4 and eventually dozens. This is where 3I/Atlas enters the story, the third confirmed interstellar visitor. Another comet, like Borisov, but with its own unique characteristics. Another opportunity to add to our growing database of these cosmic travelers. Another chance to refine our understanding of what interstellar space contains and what processes eject objects from their home star systems. But 3I/Atlas brought its own surprises. It wasn't just a repeat of Borisov. It had characteristics that puzzled scientists, behaviors that didn't quite match expectations, and it arrived at a time when our observation capabilities had improved, when instruments like TESS could be brought to bear, when coordination between ground-based and space-based assets had become more sophisticated. The scientific community was ready. They'd learned from Oumuamua and Borisov. They knew how to maximize the observational return from these brief visits. So when 3I/Atlas appeared, tracking inward toward the Sun on its hyperbolic trajectory, the response was swift and comprehensive. Every available telescope, every useful spacecraft, every spectroscopic capability, all focused on this visitor, determined to extract every possible piece of information before it departed forever. And NASA's decision to redirect TESS represented just one part of this coordinated effort, but it was a significant part, a recognition that continuous monitoring from space could reveal details that ground-based observations might miss. The context provided by Oumuamua and Borisov makes 3I/Atlas's observations more meaningful. We're not starting from zero. We have comparison points. We can ask whether 3i/Atlas resembles Borisov or Oumuamua or neither. We can look for patterns across these three visitors, tentative as those patterns might be with such a small sample size. We can begin to build a framework for understanding interstellar objects as a category, rather than treating each as a complete mystery. And that's exactly what scientists set out to do when they turned their instruments toward this third visitor, ready to see what secrets it would reveal. TESS. The name stands for Transiting Exoplanet Survey Satellite, and its primary mission defines modern planet hunting. Launched in 2018, TESS orbits Earth in a unique path that gives it unobstructed views of the sky for extended periods. Its purpose is elegant in concept: stare at stars, watch for the tiny dimming that occurs when a planet crosses in front of its host star from our perspective, and catalogue these transits to build a comprehensive map of planets throughout our galactic neighbourhood. The technique, called the transit method, has revolutionised our understanding of planetary systems. When a planet passes in front of its star, it blocks a small fraction of the star's light. For Earth-sized planets around Sun-like stars, this dimming is less than 1%. For larger planets, the effect is more pronounced but still subtle. TESS's instruments are sensitive enough to detect these tiny variations in starlight across thousands of stars simultaneously. It divides the sky into sectors, observing each sector continuously for weeks before moving to the next, slowly building a comprehensive survey of the stars visible from our location in the galaxy. This is patient work, systematic work, the kind of science that requires consistency and careful planning. TESS's observation schedule is mapped out well in advance. Each sector gets its allocated time. Each star on the target list receives the attention promised in approved research proposals. Interrupting the schedule to observe something other than stars, something much closer and moving rapidly through the solar system, goes against everything the satellite was designed to do, yet that's exactly what happened in January of this year. NASA made the decision to interrupt TESS's planet hunting and point the satellite at 3i/Atlas. For over a week, from mid-January through late January, TESS tracked the comet continuously as it moved outbound through the inner solar system. Every instrument, every sensor, focused on this single object, measuring subtle changes in its brightness, capturing variations that would reveal information about the comet's rotation, surface characteristics, and activity level. Why? What makes TESS particularly valuable for comet observations? The answer lies in continuity. Ground-based telescopes, no matter how powerful, face an inherent limitation. They can only observe at night. When the sun rises, observations stop. When weather interferes, clouds and storms block the view. These interruptions fragment observations, creating gaps in the data that can miss crucial changes happening on timescales of hours rather than days. Space-based instruments like TESS don't face these limitations. They observe continuously, day and night from their perspective, unaffected by weather or atmospheric interference. This continuous monitoring becomes especially valuable for objects like comets, which can change rapidly as they respond to solar heating. A jet of gas erupting from the surface might last only hours. A piece of the nucleus fragmenting away might be a brief event. Ground-based observers might miss these entirely if they happen during daylight or bad weather, but TESS, watching continuously, captures everything. The January observation period was carefully chosen. 3i/Atlas had already made its closest approach to the Sun back in late October of the previous year. It had rounded that Perihelion point, passed through the most intense heating, and was now moving outbound, still active but gradually cooling as it retreated to greater distances. This timing offered a sweet spot. The comet was bright enough for detailed observation, still releasing enough gas and dust to study, but past the chaotic period immediately around perihelion, when activity can be so intense that it obscures underlying characteristics. TESS captured something ground-based telescopes struggle with: the rotation rate of 3i/Atlas. As the comet tumbled through space, spinning on its axis, different parts of its surface came into sunlight and then into darkness. This rotation created a periodic variation in brightness. By measuring this variation precisely, scientists could determine how fast the comet was spinning and potentially learn about its shape. Was it elongated, like Oumuamua, or more spherical, like typical solar system comets? The brightness variations, their amplitude and period would tell the story. But here's where the story gets even more interesting. After the January observations, Scientists began looking backward through TESS's archived data, checking whether the satellite might have captured images of 3I/Atlas during earlier observation sectors before anyone knew the comet existed. They found something remarkable. TESS had indeed observed the region of sky where 3/Atlas was located back in spring of the previous year, months before the comet's official discovery. The data was there, sitting in archives, waiting to be analysed. This earlier observation occurred when 3/Atlas was much farther from the Sun, colder, less active. Comparing these early observations to the later January data would let scientists track how the comet's activity evolved as it approached and then retreated from perihelion. It was an unexpected gift, additional data that hadn't been part of the original observation plan, but which turned out to be scientifically valuable. This backward search through archives represents an increasingly common phenomenon in astronomy. Our survey telescopes capture so much data, imaging such vast swathes of sky, that they inevitably record objects we don't recognize at the time. Only later, when something becomes interesting for other reasons, do scientists go back and search for earlier observations. The archives hold countless treasures, data points waiting to be connected to discoveries made months or years later. The TESS observations didn't happen in isolation. They were part of a coordinated effort involving multiple spacecraft and ground-based observatories. Each instrument contributed something unique. Ground-based telescopes provided spectroscopic data, breaking down the light from 3I/Atlas into its component wavelengths to identify what gases were being released. Other space telescopes, including the Swift Observatory, measured ultraviolet emissions that reveal specific chemical processes. And Parker Solar Probe, NASA's spacecraft studying the Sun, happened to have a useful viewing angle during a critical period and captured images of the comet when it was nearly impossible to observe from Earth's direction. This coordination highlights how modern astronomy operates. No single instrument can do everything. Each has strengths and limitations. By bringing multiple capabilities to bear on a single target, scientists create a comprehensive picture that no individual observation could provide. TESS contributed continuous monitoring and rotation measurements. Swift provided ultraviolet spectroscopy. Ground-based observatories offered high-resolution imaging and optical spectra. Together, these observations told a richer story than any could alone. The decision to use TESS wasn't made lightly. The satellite's time is precious. Every hour spent observing the comet was an hour not spent hunting for planets. Proposals to use TESS for non-planet hunting observations face intense competition and careful scrutiny. The fact that NASA approved this observation, that they considered 3I/Atlas important enough to warrant interrupting the primary mission, speaks to the scientific value these interstellar visitors represent. What made this particular visitor worth such attention? The answer comes partly from context. With only 2 previous interstellar objects to study, each new visitor adds disproportionate value. We're still in the early stages of understanding these objects. We don't yet know what's typical and what's unusual. Every new data point refines our picture, and 3I/Atlas, as arriving with better timing and more advanced instruments available than either Oumuamua or Borisov, offered an opportunity to collect higher quality data than had been possible before. But there was also something specifically interesting about 3I/Atlas itself. Even in early observations before the TESS data, scientists had noticed unusual characteristics. The comet was surprisingly active for its distance from the Sun. Most comets remain dormant until they get relatively close to the Sun, where solar heating becomes intense enough to vaporize significant amounts of ice. But 3I/Atlas was releasing measurable amounts of water vapor while still quite far out, beyond where typical solar system comets become active. This unusual activity suggested something interesting about the comet's composition or structure. Maybe its ice was different somehow, more volatile, easier to vaporize. Maybe its surface was porous, allowing solar heat to penetrate deeply even at large distances. Maybe there was something about its formation environment in that distant star system that made it fundamentally different from comets formed in our solar system. Whatever the explanation, the unusual behavior marked 3I/Atlas as particularly worthy of detailed study. The TESS observations were meant to capture this activity in unprecedented detail. By monitoring continuously over a week, scientists could track day-to-day changes, see how the comet's brightness varied not just from rotation, but from changes in activity level, potentially catch short-lived events like outbursts or the release of fragments. The data would complement what ground-based observers were seeing, filling in gaps, providing continuous coverage that revealed the full behaviour of this interstellar visitor. There was one technical challenge during the observation period worth mentioning. TESS briefly entered what's called safe mode, a protective state that spacecraft automatically adopt when their computers detect something potentially wrong. This pause in observations lasted only briefly before controllers restored normal operations, but it represented the kind of real-world complication that affects space missions. Not everything goes perfectly. Systems hiccup, engineers troubleshoot and recover. The important thing is that the observations resumed and ultimately succeeded in capturing the delta scientists needed. When the test data finally came down, when scientists began analysing those continuous brightness measurements, they added another piece to the puzzle of 3I/Atlas. The comet was revealing itself slowly through multiple observations by multiple instruments, each contributing part of the story. But to truly understand what 3I/Atlas is and what it means, we need to follow its physical journey through our solar system, trace its path from discovery through Perihelion and back outward, understand how solar heating activated it, and what happened during those critical months when it was most accessible to our instruments. Every visitor has a path, and 3I/Atlas's path through our solar system tells its own story. From the frozen outer darkness where it first appeared in our telescopes, through the inner regions where the sun's heat awakened it, and back out toward the cold from which it came. The comet's journey spans the full range of environments our solar system offers. Tracing this path helps us understand not just where the comet went, but how it changed along the way. When astronomers first detected 3I/Atlas, it was already inside our solar system, having crossed some invisible boundary where the sun's influence begins to dominate over interstellar space. But it was far out beyond the orbit of Jupiter, that giant planet whose gravity shepherds so many objects in our cosmic neighbourhood. At that distance, the sun appears merely as a bright star rather than the blazing disk we see from Earth. Solar heating was minimal. The comet remained dormant, frozen, carrying the cold of interstellar space in its ancient ice. As it moved inward, following the hyperbolic trajectory that would carry it through our system and out again, the sun's influence grew stronger, not just gravitationally, though the sun's gravity certainly bent the comet's path, pulling it into a curved trajectory that would eventually swing around and send it back outward, but also thermally. The sun's radiation, weak at first, began warming the comet's surface. Ice, frozen solid for millions or billions of years, started to feel heat it hadn't experienced since leaving its home star system. The transition from dormant to active happens gradually for comets. There's no specific distance where a switch flips. Instead, as solar heating increases, the warmest parts of the surface, the regions facing the sun most directly, reach temperatures where ice begins to sublimate, transforming directly from solid to gas without passing through a liquid phase. This gas escapes from the surface, carrying with it tiny particles of dust that were embedded in the ice. Together, the gas and dust form the coma, the fuzzy atmosphere that surrounds the solid nucleus and gives comets their characteristic appearance. For 3I/Atlas, this activation happened earlier than it does for typical solar system comets. Even while still quite distant, instruments detected signs of activity. Water vapor, the most common component of cometary gas, appeared in spectra. The comet was waking up, responding to solar heating despite being farther from the sun than most comets when they become active. This early activity marked the comet as interesting, suggesting something different about its composition or structure. The inbound journey continued through late summer and into autumn of last year. The comet moved through the asteroid belt, that zone between Mars and Jupiter, where countless rocky bodies orbit in the sun's gravitational grip. But 3I/Atlas wasn't part of that population. It was just passing through, a temporary visitor among permanent residents. Its trajectory aimed it toward the inner solar system, toward a date with Perihelion that would come in late October. Perihelion, the closest approach to the sun. For any comet, this represents the critical moment. Solar heating reaches maximum intensity. Whatever ice remains on or near the surface vaporizes rapidly. Activity peaks. The coma expands. If the comet has enough gas production, a tail forms. That beautiful streaming of gas and dust pushed away from the sun by solar wind and radiation pressure. For 3I/Atlas, Perihelion came on October 29th. At its closest, The comet passed just inside the orbit of Mars, coming closer to the Sun than the red planet, but still maintaining a comfortable distance. Nothing like the sun-grazing comets that occasionally plunge deep into the solar atmosphere. This perihelion distance was actually ideal for scientific observation. Close enough that solar heating activated the comet strongly, releasing significant gas and dust for instruments to analyze, but not so close that the comet risked disruption or destruction from intense solar radiation. Some comets pass so near the Sun that they simply vaporize, torn apart by tidal forces and thermal stress. 3. I/Atlas faced no such danger. Its perihelion was active but safe, allowing the comet to survive and continue outbound after rounding the Sun. But here's where the geometry of the solar system created an observational challenge. As 3I/Atlas approached and then passed through perihelion, its position in the sky, as viewed from Earth, brought it increasingly close to the Sun's apparent location. From our perspective, the comet was moving into the solar glare, that region of sky so dominated by the Sun's brightness that telescopes cannot observe there. For several weeks around perihelion, the comet was essentially invisible to Earth-based instruments. It was there, continuing its journey, reaching maximum activity, but hidden from our direct observation by the Sun itself. This is where spacecraft in different locations become invaluable. Parker Solar Probe, orbiting much closer to the Sun than Earth, had a different viewing angle. During the period when 3I/Atlas was hidden from Earth, Parker could still observe it, capturing images that ground-based telescopes couldn't obtain. These observations filled a critical gap, documenting the comet's behavior during its most active period, ensuring that scientists didn't miss this crucial phase of its evolution. By December, 3I/Atlas emerged from solar glare, reappearing in Earth's evening sky. Observers who'd been forced to wait now eagerly resumed their studies. Telescopes locked onto the comet, measuring how its activity had changed, comparing its appearance to observations made before perihelion. The comet was noticeably brighter, more active, releasing more gas and dust as the Sun's heat penetrated deeper into its nucleus, vaporizing ice that had remained frozen during the inbound journey. Late December brought another significant moment, closest approach to Earth. This didn't mean the comet passed dangerously near our planet. The distances in the solar system are vast, and 3I/Atlas's trajectory kept it well away from any planetary collision. But from an observational standpoint, this closest approach mattered. The nearer an object is, the more detail telescopes can resolve, the brighter it appears, the easier it becomes to study. Scientists timed intensive observation campaigns to coincide with this optimal viewing period. This was when TESS entered the picture, adding continuous monitoring to the mix of ground-based observations happening globally. The comet was moving outbound but still relatively close, still active enough to be scientifically interesting, but past the chaotic peak of activity that had occurred around perihelion. Perfect conditions for detailed study. As January progressed and TESS completed its observation campaign, 3I/Atlas continued its outbound journey. It passed back through the inner solar system, crossing Earth's orbit, then Mars's orbit, heading toward the outer system. All the while, it was gradually cooling. The Sun's heat, intense at perihelion, weakened with increasing distance. The comet's activity began to decline, less gas released, less dust carried away. The coma, which had expanded to impressive size around perihelion, started to shrink. By now, months after those critical observations, 3I/Atlas has travelled even farther outward. It's approaching Jupiter's orbital distance, moving back into the cold outer regions from which it arrived. The activity that characterized its passage through the inner system has largely ceased. The comet is returning to dormancy, its surface ice refreezing, locking away whatever material remains beneath the protective crust formed by solar heating. But the journey continues. 3I/Atlas will keep moving outward, past Jupiter, past Saturn, eventually past Neptune and Pluto, into the distant regions where the Sun's influence fades towards zero. There's no force that will stop it or turn it around. Its velocity remains above escape velocity. Years from now, it will cross the boundary where our solar system ends and interstellar space begins, returning to the dark ocean from which it came. Only now it will be slightly warmer than when it arrived, having absorbed a tiny amount of heat during its brief passage near the Sun. And it will be slightly lighter, having lost some mass through the gas and dust released during its active phase. Where will it go next? The galaxy rotates. Stars move. Predicting the distant future path of 3I/Atlas with precision is impossible because we can't perfectly account for every gravitational influence it will encounter over millions of years, but we can say with certainty that it will continue wandering through interstellar space. Perhaps millions of years from now it will pass through another star system, giving astronomers orbiting another planet the same brief opportunity to study an interstellar visitor that we've had. Perhaps it will drift forever, never again coming near a star, remaining frozen and dormant for the rest of time. Its journey through our solar system, brief as it was on cosmic timescales, gave us a window into this wanderer's nature. The observations made during those critical months, especially around perihelion and during the January TESS observations, captured data that scientists will analyse for years. That data, those measurements, they tell us what 3I/Atlas is made of, where it likely came from, and what its presence suggests about the universe beyond our small corner of it. And that's what we need to explore next. What scientists actually discovered about this visitor, what the data revealed, what secrets this ancient comet carried in its ice. Data from telescopes and spacecraft tell stories, but you have to know how to read them. The light captured by instruments, broken into spectra, measured for brightness variations, analysed for chemical signatures, contains information about objects millions of miles away. For 3I/Atlas, this data revealed a portrait of an interstellar comet that was both familiar and surprising, fitting expectations in some ways while challenging assumptions in others. The most fundamental discovery came from ultraviolet observations. The Swift Observatory, a space telescope designed to study high-energy phenomena across the universe, turned its instruments toward 3I/Atlas as the comet moved through the inner solar system. In ultraviolet wavelengths, certain gases glow with characteristic signatures. Water vapor, when broken apart by solar ultraviolet radiation, produces a telltale emission from hydroxyl radicals, the OH fragments that result from water molecules being split. Swift detected this hydroxyl emission clearly and strongly. The comet was releasing water. This might not sound revolutionary, after all. We know comets contain ice. That's what makes them comets rather than asteroids. But confirmation matters in science. With interstellar objects, we can't assume anything. Oumuamua hadn't shown obvious water emissions, which contributed to debates about whether it was truly a comet or something else. Borisov had shown water, establishing that at least some interstellar comets contain familiar chemistry. Now 3I/Atlas confirmed water again, adding another data point to suggest that water might be common in interstellar comets, that ice formation around other stars produces the same basic substance we find in our solar system comets. But the interesting part wasn't just that water was present, it was how much and when. Scientists measured the rate at which 3I/Atlas was releasing water, calculated from the strength of those hydroxyl emissions. Yeah, the comet was surprisingly productive. Even at fairly large distances from the Sun, where solar heating should be relatively weak, it was releasing substantial amounts of water vapor. This high activity level suggested something about the comet's composition or structure. One possibility is that 3I/Atlas contains particularly volatile ice, perhaps mixed with more reactive compounds that sublimate easily even without intense heating. Another possibility is that its structure is highly porous, like a sponge, allowing solar heat to penetrate deeply into the nucleus instead of being absorbed just by the outer surface layer. A porous structure would let heat reach buried ice, creating gas release from beneath the surface rather than just from the outermost crust. This porosity concept connects to ideas about how comets form. In the outer regions of planetary systems where temperatures are extremely cold, ice doesn't freeze into solid blocks. Instead, individual ice particles grow slowly, eventually clumping together gently to form larger bodies. This gentle accretion can create structures with lots of empty space between particles, resulting in a comet nucleus that's more like compressed snow than solid ice. If 3I/Atlas formed this way, in the cold outer regions of whatever planetary system ejected it, its porous structure would explain why solar heat affects it so efficiently. The chemistry revealed by spectroscopic observations added more detail to the picture. Besides water, instruments detected other molecules being released from the comet. These observations are technically challenging because cometary spectra are complex, with many overlapping features from different molecules, but careful analysis can tease apart these signatures, identifying individual compounds. For 3I/Atlas, The detected molecules suggested chemistry similar to what we see in solar system comets. Simple compounds, the kind that form in cold environments where available elements combine in straightforward ways. This chemical similarity might be the most profound discovery. It suggests that planetary formation, comet formation specifically, works similarly around different stars. The basic processes, the physics and chemistry that govern how dust and ice come together to form comets, appear to be universal. Whether a comet forms in our solar system or in a system hundreds of light years away doesn't fundamentally change what it's made of. This universality makes sense from a physics standpoint, but confirmation through actual observation of interstellar material matters enormously. It's the difference between theoretical expectation and empirical fact. Scientists also studied the dust released by 3I/Atlas. As gas escapes from the nucleus, it carries tiny dust particles with it, grains that were frozen into the ice when the comet formed. These grains scatter sunlight, creating the visible coma and tail. But not all scattering is the same. The way light scatters depends on the size and composition of the particles. By measuring this scattering carefully, astronomers can infer properties of the dust. For 3I/Atlas, the dust appeared similar to dust from solar system comets. Grains of various sizes, composed primarily of silicate minerals, the rocky compounds that form from silicon and oxygen combining with other elements. This dust likely condensed in the disk of material surrounding 3I/Atlas's home star billions of years ago, the same kind of disk that surrounded our Sun when our solar system formed. The grains got incorporated into growing ice particles, eventually becoming part of the comet nucleus, and have been locked in that frozen prison ever since, preserved in interstellar space until solar heating freed them. There was also something about the comet's colour. When observed in visible light, 3I/Atlas appeared somewhat reddish. This coloration comes from organic compounds, complex carbon-based molecules that form in space through various chemical processes. Solar system comets often show this reddish tint, caused by organic material coating their surfaces or mixed into their ice. The fact that 3I/Atlas shows similar colour suggests these organic compounds are common in comets regardless of where they form. This has implications for astrobiology, the study of life's potential existence beyond Earth. Organic compounds aren't alive, but they're the chemical building blocks from which life can potentially emerge. If comets throughout the galaxy carry these compounds, if they're delivering this material to planets wherever comets impact surfaces, then the raw ingredients for life might be widely distributed across the cosmos. Every planetary system might be getting seeded with organic chemistry through comet impacts, just as Earth likely was in its early history. The observations also revealed something about the comet's nucleus, the solid body at the heart of all that gas and dust. Determining the exact size is difficult because we can't directly image something so small at such distances. Instead, scientists estimate size from brightness, knowing approximately how reflective comet surfaces are. For 3I/Atlas, these estimates suggest a nucleus somewhere around a few kilometers across. Not tiny, but not enormous either. Comparable to many solar system comets. The brightness variations captured by TESS and other instruments suggested the nucleus is rotating, tumbling through space as it orbits. This rotation causes different parts of the surface to come into and out of sunlight, creating the periodic brightness changes that TESS was designed to detect. The exact rotation period, how long it takes the comet to complete one spin, requires careful analysis of those brightness curves. Scientists are still working through this data, but preliminary indications suggest a rotation period measured in hours, typical for comet-sized bodies. Rotation tells us something about the comet's history. Objects in space acquire their spins through various processes. Impacts can set bodies rotating. Gravitational interactions during close passes of planets can change rotation rates. For 3I/Atlas, its current rotation likely reflects some combination of its formation process and whatever gravitational interaction ejected it from its home system. That ejection event, when whatever planetary giant flung this comet into interstellar space, probably affected its spin, either speeding it up or slowing it down or changing its rotational axis. One question that observations tried to answer was whether 3I/Atlas showed any signs of fragmentation. Comet nuclei aren't always structurally strong. They can break apart under stress, either from rapid rotation creating centrifugal forces or from internal pressure building up as ice vaporizes beneath the surface. When a comet fragments, it creates multiple brightness peaks in the coma, as several pieces each release their own gas and dust. Careful observers watch for these signatures of splitting. For 3I/Atlas, the observations don't show clear evidence of major fragmentation. The comet appears to have remained intact throughout its passage through the inner solar system. This structural integrity suggests the nucleus is either strong enough to resist disruption or hasn't experienced forces sufficient to tear it apart. Either way, it means the object we're studying is probably a single coherent body rather than a loose cluster of fragments. But here's the honest scientific truth. Despite all these observations, despite the coordinated efforts of multiple telescopes and spacecraft, despite the intensive study, many questions about 3I/Atlas remain unanswered. We don't know exactly where it came from with high precision. The trajectory points toward a general direction, but identifying a specific home star is probably impossible. We don't know exactly how old it is. Billions of years seems likely, but whether it's as old as our solar system or younger or even older remains uncertain. We don't know whether it ever had close encounters with other stars during its interstellar journey. Depending on where it wandered and what paths it took through the galaxy, suns it might have passed near other stellar systems, might have felt their gravitational influences, might have been observed by hypothetical astronomers on other worlds, or it might have drifted through empty regions far from any stars, experiencing nothing but the gentle pull of the galaxy's overall gravitational field. We don't know whether its composition is truly typical of interstellar comets, or whether 3I/Atlas represents some particular subcategory. With only 3 confirmed interstellar visitors to study, we can't yet establish what typical means. Maybe most interstellar comets are like Borisov, and 3I/Atlas is an outlier. Maybe 3I/Atlas is typical, and Borisov was unusual. We need more examples to answer these statistical questions. These uncertainties don't diminish the value of what was learned. Science progresses through accumulating knowledge, through adding piece after piece to an emerging picture. Each new observation constrains possibilities, rules out some hypotheses while supporting others, gradually narrowing the range of what's plausible. 3I/Atlas added crucial pieces to this puzzle. It confirmed that water-bearing interstellar comets exist, that their chemistry resembles solar system comets, that they become active in ways we can measure and understand. The data scientists collected will be analysed for years. Researchers will extract every possible insight, will compare 3I/Atlas to the previous interstellar visitors and to solar system comets. We'll use the measurements to refine models of comet formation and planetary system evolution. Papers will be published, findings will be debated. New questions will emerge from answers to old ones. This is how science works, not through single definitive discoveries, but through gradual accumulation of evidence and understanding. But beyond the technical details, beyond the spectroscopic measurements and brightness curves and chemical abundances, there's a deeper significance to what 3I/Atlas represents. This comet, with its ancient ice and interstellar origins, connects us to the broader universe in a way few things can. It's not just data, it's a physical visitor from beyond, a tangible piece of the galaxy that we could touch if we could reach it. And what it tells us matters not just for planetary science, but for how we understand our place in the cosmos. That's what we need to explore next. Why these interstellar visitors matter beyond the scientific details. What they mean for humanity's broader understanding of the universe we inhabit. Scientific discoveries mean little if they remain locked in technical papers, understood only by specialists. The real value comes from connecting those discoveries to larger questions, to the fundamental curiosities that drive human inquiry about existence and our place in the cosmos. 3. I/Atlas, with its ancient ice and interstellar origins, connects to some of the most profound questions we can ask. Why does this single comet, passing briefly through our solar system, matter beyond being an interesting astronomical observation? Start with the concept of cosmic perspective. For most of human history, we thought our solar system was isolated, unique, perhaps the only planetary system in existence. The universe beyond consisted of stars, unreachably distant, and fundamentally different from the familiar planets orbiting our sun. That perspective has dissolved over recent decades. We now know planetary systems are common, perhaps universal. Most stars have planets. The galaxy teems with worlds, but knowledge and experience are different things. Knowing intellectually that other planetary systems exist doesn't create the same visceral connection as having actual material from those systems arrive in our neighbourhood. Interstellar visitors like 3I/Atlas make the reality tangible. This isn't theoretical, it's real ice, real rock, real dust from a place that formed around another star. We can point telescopes at it. We can measure it. We can study it directly. That directness transforms abstract knowledge into concrete reality. These visitors also demonstrate that planetary systems aren't isolated islands. They exchange material. When planets eject comets during their formation process or through later gravitational interactions, those comets don't just disappear. They wander through the galaxy, occasionally encountering other stellar systems. 3I/Atlas arrived here carrying material from wherever it formed. Eventually, when it departs, it will carry something new. The subtle warmth of having passed near our Sun. The tiny bit of additional velocity imparted by our solar system's gravity. It becomes, in a sense, a messenger that has visited our system. And if comets from other systems can reach us, then comets from our system can reach other stars. Right now, wandering through interstellar space, there are probably comets ejected from our solar system millions or billions of years ago. Some might eventually pass through other planetary systems. If those systems host civilizations with telescopes and curiosity, they might study those comets the way we've studied 3I/Atlas. They might learn about our solar system through analyzing material that formed here. The galaxy facilitates this exchange, this cosmic mixing of material between stellar systems. This exchange matters for understanding how life emerges. One of the great questions in astrobiology is whether life's origin requires some special circumstance unique to Earth, or whether it emerges naturally wherever conditions allow. The answer depends partly on whether the chemical building blocks for life are rare or common. If they're rare, limited to unusual environments, then life might be correspondingly rare. But if they're common, distributed widely throughout the galaxy, then life's emergence might be common too. Interstellar comets provide evidence on this question. The organic compounds detected in 3I/Atlas and Borisov, the same kinds of compounds found in solar system comets, suggest that organic chemistry develops naturally in planetary systems. It's not unique to Earth or our solar system. Wherever comets form in cold outer regions of planetary systems, they likely incorporate organic material. And since comets occasionally impact planets, delivering their contents to planetary surfaces, every solar system with comets probably experiences organic compound delivery to its planets. On Earth, we know comets and asteroids heavily bombarded the surface during our planet's early history. Some of these impactors likely delivered water, helping form our oceans. Others delivered organic compounds, contributing to the chemical richness from which life eventually emerged. This process probably wasn't unique to Earth. Every rocky planet in every planetary system probably experiences similar bombardment. If those impactors carry water and organic compounds as commonly as 3I/Atlas's composition suggests, then every planetary system is getting seeded with life's potential building blocks. This doesn't mean life is inevitable. Chemistry alone doesn't create biology, but it means the ingredients are probably available widely. The next steps, from chemistry to self-replicating molecules to actual life, might still be rare and difficult, but at least the starting materials are there, scattered throughout the galaxy by the same processes that created and ejected objects like 3I/Atlas. There's also something profound about time contained in these visitors. 3I/Atlas's ice formed billions of years ago in conditions of extreme cold. The molecules in that ice, the dust grains frozen within it, they're ancient beyond human comprehension. They preserve information about the early history of whatever planetary system created them. When scientists analyze the isotopic ratios in that ice, the relative abundances of different forms of atoms, they're looking at signatures that formed when that distant solar system was young. This is time travel of a sort. We can't physically visit the past, but we can study material preserved from ancient times. 3I/Atlas is a time capsule, carrying information from an era and place we could never otherwise access. Its ice might have formed when the universe was younger, when the galaxy had a different structure, when the mix of elements available for planet formation was different from what we see in our solar system. Each interstellar visitor adds to our understanding of cosmic history, showing us snapshots of conditions in different places and times. The increasing frequency of these detections tells another important story. Oumuamua in 2017, Borisov in 2019, now 3I/Atlas, 3 confirmed interstellar visitors in less than a decade. This might seem like a slow rate, but remember that our detection capabilities have only recently become good enough to spot these objects. We're almost certainly missing many more that pass through too far from the Sun, or too faint for our instruments, or simply at the wrong time when nobody's looking in that direction. Statistical models, based on the handful we have detected, suggest that interstellar objects might pass through the inner solar system fairly frequently. Maybe several per year, maybe more. The space between stars isn't as empty as we thought. It's filled with wanderers, with debris from planetary systems throughout the galaxy, objects drifting on journeys that might last billions of years. We're only now becoming aware of this hidden population, this cosmic background of interstellar material flowing past us. As our detection capabilities improve, as survey telescopes become more powerful and comprehensive, we'll spot more of these visitors. The next generation of astronomical instruments, massive telescopes currently under construction, will be able to detect fainter and more distant objects. Survey systems designed specifically to spot fast-moving interstellar visitors are being planned. Within the next decade or two, we might go from having a handful of confirmed interstellar objects to having dozens or hundreds. That statistical sample will transform our understanding. With enough examples, we can start answering questions that are currently unanswerable. What fraction of interstellar visitors are comets versus asteroids? Do they come predominantly from certain directions, or uniformly from all parts of the galaxy? Are there different populations with different characteristics? What does the size distribution look like? All these questions require numbers. Enough examples to establish patterns and test hypotheses. There's also the practical angle of planetary defense. While 3I/Atlas posed no danger to Earth, passing nowhere near our planet's orbit, future interstellar visitors might. An object arriving from outside the solar system on a collision course with Earth would present unique challenges. Its trajectory would be harder to predict precisely because we wouldn't have years of prior observations to refine our orbital calculations. Its composition might be uncertain, affecting how we'd assess impact consequences. Understanding interstellar visitors better now, while there's no immediate threat, prepares us for the possibility of a future visitor that does pose danger. But perhaps the most important reason these visitors matter has nothing to do with practical applications or answering specific scientific questions. It's about maintaining wonder. In an age where so much feels mundane, where daily experience rarely touches the genuinely extraordinary interstellar visitors, remind us that we live in a universe full of marvels. An object that formed around another star, that wandered through space for eons, that arrived at our doorstep carrying secrets from unimaginable distances. This is the stuff of science fiction made real. When you look up at the night sky, those stars aren't just distant lights. They're places. They have planetary systems. They create comets and asteroids through the same processes that shaped our solar system. Some of those comets get ejected, sent wandering through the galaxy. And sometimes, rarely but repeatedly, one of those wanderers passes through our neighborhood. We're connected to those distant systems in ways both physical and philosophical. 3I/Atlas, in its brief passage through our solar system, served as ambassador from that larger universe. It reminded us that our cosmic neighborhood isn't isolated. It demonstrated that the galaxy is dynamic, full of material in motion, with objects constantly exchanging between systems. It showed us that the chemistry forming planets and comets works similarly throughout the galaxy. And it challenged us to think bigger, to recognize that our solar system is just one among hundreds of billions, that the universe extends far beyond what we can directly explore. These are lessons worth learning. They're perspectives worth maintaining. And they're reasons why NASA chose to redirect TESS, why observatories worldwide coordinated their efforts, why scientists devoted months to studying this single comet. Not just because of what it could teach us technically, though that matters, but because of what it represents, a connection to the cosmos that surrounds us, a physical reminder that we're part of something vastly larger than ourselves. And now, as 3I/Atlas departs, heading back to the darkness from which it came, we're left with one final chapter to consider: the farewell, the reflection on what this brief encounter means as the visitor vanishes back into interstellar space. There's something melancholy about endings, even when we know they're inevitable. 3I/Atlas is leaving. By now, as you listen to this, the comet has travelled far beyond the inner solar system where all those critical observations took place. It's crossed back outward past the orbit of Mars, past Earth, moving steadily toward the outer regions where the sun's warmth fades into the perpetual cold that dominates most of space. Each day carries it farther away. Each week puts more distance between this visitor and the star it briefly approached. The activity that characterized its passage through the inner solar system has largely ceased. Without the sun's heat to vaporize ice, The gas production has stopped. The coma that surrounded the nucleus, that fuzzy atmosphere of gas and dust, has dissipated. The comet has returned to dormancy, its surface refreezing, locking away whatever volatiles remain beneath the protective crust. To telescopes on Earth, it appears as nothing more than a faint point of light, growing dimmer with each passing night as increasing distance reduces its brightness. Soon, it will fade below the detection threshold of even our most powerful instruments. We'll lose track of it against the background of distant stars. The trajectory has been calculated well enough that we know where it's going in general terms, but precise tracking will become impossible once it grows too faint to observe. From that point forward, 3I/Atlas will continue its journey unseen by human eyes, unwatched by our instruments, returning to the anonymous state it occupied for millions or billions of years before entering our solar system. It will be years before it crosses the orbit of Neptune. Decades before it reaches the outer boundary where our sun's influence truly ends and interstellar space begins. By the time it makes that transition, everyone currently working on 3I/Atlas observations will have moved on to other projects, other comets, other mysteries demanding attention. The comet will become a footnote in astronomical databases, a set of measurements and observations archived for future researchers who might someday find new insights in old data. Where will it go after leaving our solar system? The galaxy rotates majestically, carrying stars and planetary systems in grand orbital patterns around the central core. 3I/Atlas will drift through this rotating galaxy, its path slowly curving under the collective gravitational influence of billions of stars. It might pass relatively near other stellar systems during its wanderings. It might spend millions of years in regions far from any star, cold and alone in the dark spaces between. The specifics are unpredictable over such timescales, but one thing is certain: it will never return here. This finality makes the observations we conducted precious. They're all we'll ever have. The data collected during those brief months when 3I/Atlas was accessible represents humanity's complete record of this visitor. Future generations won't be able to check our measurements or conduct new observations if questions arise. What we captured is what we have. The spectra showing water and other compounds, the images revealing the comet's coma and structure, the brightness measurements tracking its rotation and activity. These are permanent records, irreplaceable pieces of evidence that will inform our understanding for decades to come. But they're also incomplete records. Despite the intensive observation campaign, despite the coordination between multiple telescopes and spacecraft, there are things we didn't learn, questions that remain unanswered, mysteries that will persist because we ran out of time before we ran out of curiosity. What was the comet's exact rotation period? The data will eventually yield this answer, but the analysis continues. What was its precise composition? The detailed inventory of compounds locked in its ice. We know water was there, we detected other molecules, but a complete compositional profile remains elusive. What was its internal structure? Did it have a solid core beneath a layer of porous ice, or was it homogeneous throughout? We inferred some structural properties from its activity pattern, but direct knowledge would require more than remote observations can provide. And where exactly did it come from? We know the general direction, towards Sagittarius and the galactic disk, but identifying a specific stellar system of origin is probably impossible without better data than we could collect. These gaps don't represent failure. They represent the inherent limitations of studying objects we can only observe briefly from enormous distances. We did remarkably well with the tools available. Humans built instruments sensitive enough to detect subtle emissions from a comet millions of kilometers away. We coordinated observations across multiple facilities. We extracted meaningful information from photons that traveled vast distances to reach our telescopes. The fact that questions remain simply acknowledges that the universe is complex and our capabilities, while impressive, are still limited. Future interstellar visitors will give us more chances. The techniques refined on 3I/Atlas, the coordination protocols developed, the understanding of what measurements matter most, all of this prepares us for the next visitor and the one after that. Each encounter teaches us how to observe more effectively, what questions to prioritize, how to maximize scientific return from these brief opportunities. We're learning how to study interstellar objects, developing expertise that didn't exist before Oumuamua arrived, and shocked us with the realization that we'd been missing these visitors all along. There's something poignant about being the generation that first becomes aware of these cosmic visitors. For all of human history before roughly 2017, We didn't know interstellar objects passed through our solar system. We couldn't detect them. We had no idea this population existed. Then suddenly we did. We saw Oumuamua and realized the universe had been sending us messengers forever. We just hadn't noticed. Now we're noticing. Now we're watching. Now we're studying these visitors while we can, extracting their secrets, learning from their ancient ice. Our descendants centuries from now will probably take interstellar visitors for granted. Their telescopes will be more powerful. Their detection systems will be more comprehensive. They might spot dozens or hundreds of these objects every year. They'll have statistical samples large enough to answer questions we can barely frame with our handful of examples. But we're the first. We're the generation that discovered this phenomenon, that began the systematic study of interstellar material passing through our cosmic neighbourhood. There's something special about being first, about pioneering new understanding. 3I/Atlas represented one moment in that pioneering effort. One comet among what will eventually be hundreds or thousands studied. But it mattered. It added crucial data to our emerging understanding. It confirmed that water-bearing comets from other stellar systems exist and behave in ways we can study and comprehend. It showed that NASA's decision to redirect TESS to interrupt planet hunting for comet observation could yield valuable science. It demonstrated that coordination between ground-based and space-based instruments creates observational possibilities that neither could achieve alone. And it reminded us, in the most concrete way possible, that the universe is vast and old and full of wonders we're only beginning to discover. Somewhere in the galaxy right now, another comet is being ejected from its home system, flung into interstellar space by a gravitational interaction with some distant planet orbiting some distant star. That comet will wander for eons, drifting through the darkness, until perhaps, millions of years from now, it passes through our solar system, or some other solar system, or maybe it drifts forever, never encountering another star. The universe doesn't care about our observation schedules or our curiosity. It operates according to physical laws, indifferent to whether anyone watches. Comets form, get ejected, wander, perhaps occasionally encounter other systems. This process has been happening for billions of years and will continue for billions more. We just happen to be here now, at a moment in time when our technology has advanced enough to notice these visitors and study them. It's a privilege, really, a cosmic coincidence that we exist at a time and in a civilization capable of seeing what earlier generations could not. As 3I/Atlas fades into the distance, growing fainter and smaller until it disappears from even our best telescopes, we're left with memory and data and wonder. The memory of those months when an interstellar visitor graced our solar system. The data captured by instruments turned toward this ancient traveller. And the wonder that comes from contemplating deep time, vast distances, and our small place in an enormous dynamic universe. The comet doesn't know we studied it. It has no awareness of the telescopes pointed its way, or the scientists analysing its composition. It simply continues its journey, following the path physics dictates, returning to the darkness that has been its home for most of existence. But we know. We witnessed its passage. We measured its properties. We added it to the growing catalogue of interstellar visitors that reminds us how much there is still to learn about the cosmos. And perhaps that's the real lesson. Not any specific fact about 3I/Atlas's composition or trajectory, but the broader recognition that curiosity drives us to notice these visitors, to study them, to extract meaning from their brief appearance in our skies. We are a species that looks up, that asks questions, that builds instruments to extend our senses beyond what biology provides. That coordinates globally to study phenomena that will never directly affect our daily lives, but that speak to deeper questions about existence and our place in the universe. 3I/Atlas has left, but the universe will send more messengers. We'll be watching.